Welcome to Chemistry 112. Today we're going to finish practice test 4, which was like the take-home test for last year. We're going to talk about what all could be involved on this coming test. I know the test is Thursday at 7 p.m. However, if that time does not work, let me know. Come take it early. I'm not sure what I'm going to be doing in class this Thursday. So you could easily come in and try to take it at that time. You could take it during any of the lab periods. I really don't care. I mean, it's just a matter of let's try to get it this week if we can. I know I have one person on who might have a little bit of issue due to sports, but we'll figure it out. We'll figure it out. This is the last test, and then we'll be prepping for the final, which is going to cover all the material. So it'll be just here and there. I'm not even sure how much of the other the review material I will record. I guess I can record bits and pieces and put in small little like summary videos per chapter. I don't know how we're going to do it, but we'll do that. That's kind of more or less a plan of what we're going to be doing. Don't forget there is an assignment due tonight. Reading is the big part. 2 things for the electrochemistry reading chapter. I think a learning curve. I know on Achieve it says 20 points, but it really should say 25. I'm just being lazy and I'm not changing it. But in the grade book, it's actually going to read 25. So it's still worth the same amount of points, and there might be an assignment. Remember, the reading is the only thing you cannot make up. Everything else you can make up. So if, for example, you have an old assignment that you're struggling on, you can still get help and do those later. If you have an old learning curve you haven't done, at some point I'll go back and check and see whether you've done it, and I've been slowly updating those. Also, don't forget in lab, there are 3 online labs. Those are in addition to the labs we're going to have. So be working on those. Get those in. As I said, you can turn them in as a group. I really don't care. Group of 2. Limit it to a group of 2. But get those done. We only have like about 2 weeks left. In lab, we're going to skip the determination of the Ka of a weak acid, and we're going to go straight to the thermodynamics one. That lab is not super hard, but we're going to use the temp probe again. We're going to weigh out an exact mass of potassium nitrate, and we're going to dissolve it in more and more water. We're going to add an exact amount of water to the best of our abilities each time and seeing what temperature does it precipitate. What temperature does it, well, what temperature does it not fully dissolve, but what temperature does it crash back at? So we're going to heat it up so it becomes a fully saturated solution and fully dissolves, and then cool it down and it's going to crystallize again. And depending on how much water it is will depend on the temperature at which it crystallizes. And you're going to find out, real easily, what is the KSP? And then we're going to use that KSP value to find the delta G and the delta H and T delta S. We're going to use our Excel again. Once again, I will walk you through the steps we can do for that. But knowing how to use Excel will make this a lot easier than it would if we, say, try to do this by hand, because it's a lot of data that has a lot of repetition, because KSP is going to be what? We're going to take the mass. We're going to divide it by its molar mass to get the moles. That's not going to change. What is going to change is the volume each time. And the volume, so the molarity is going to be then your moles divided by volume. And your KSP is going to be equal to what? KSP is going to be, because it's potassium nitrate, it's going to be the molarity squared. And so the KSP is going to change a little bit each time when the volume changes. And then you can relate that KSP with its temperature to delta G by the delta G equals negative RT ln KSP. And then there are some other steps we're going to go through, but that's going to be a little bit later. Okay, we'll go ahead and get started. We'll work on finishing this test, and then we'll make a quick summary of what all the types of equations and types of problems we can see and deal with. And if you have any questions, please bring them up. Okay. The first problem of the last page was, I think we finished problem 6 last week, which was the combustion of ethanol, determine the enthalpy of the reaction, which we just simply looked up the values. We might have had to look up ethanol on a different source. And then without calculating, figure out the entropy, whether it's positive or negative. And that you're looking at, you would have 3 moles of gas on the left and 5 moles of gas on the right. And the general idea is the number of moles of gas will determine the entropy. So we have an increase of 2 moles of gas. So we should see a net increase in entropy. The same way in chapter, the thermodynamics chapter, where we learned about work and heat and delta H for the first time, you could look at the work would increase when there's more moles of gas on the right. The same way, the entropy will increase when there's more moles of gas on the right. But okay, we were on problem 7, that the sublimation of ammonia and chloride related to the following problem. So ammonium chloride solid. Sublimation is when we go from solid to gas without passing through the liquid phase. So we have the reaction that, except ammonium chloride doesn't stay ammonium chloride, it splits into NH3 and HCl. Both gases, both not very nice to breathe in. So the first question is, above what temperature will this reaction occur? And then 2, what concentration of ammonia would be present from the natural decomposition at 25? So we can find the K value. So now, what temperature will this occur requires us to find delta H and delta S, because the only equation that we can use to find these two comes from the idea that we want, when will this be spontaneous? Will it be spontaneous when Gibbs is equal to 0? When Gibbs is equal to 0, we're saying delta H minus T delta S is equal to 0. And so solving for temperature, you would get delta H over delta S is equal to T. So we're finding the point where what is delta H over delta S? But to do that, we need to find what is the delta H of ammonium chloride solid, what is the delta H of ammonia, what is the delta H of hydrochloric acid gas, what is the delta S, all that fun stuff. So now we'll go into our thermodynamic table. So remember, this is alphabetically, so this is probably under nitrogen and hydrogen. Hydrogen will give us, no, it might be, the hydrochloric acid might be under chlorine. Oh, okay. We'll have some time to try to find that in a bit. Worst case scenario, I will look at different source. Once again, this may not be the best source, but this at least gives us ammonium chloride. Remember, the first number is typically the delta H, the second number is the delta G, and the last number is the delta S. So delta H, delta S for ammonium chloride is 314.43 and 94.6. Now for ammonia, we don't want aqueous, we want ammonia gas. This doesn't have that either. This one is proving to be, no. Let's say let's see. Chlorine. Hydrogen, well, here's at least a delta H of hydrogen chloride. That doesn't give me the entropy, but gives me at least a delta H. Let's see if I can find ammonia. Ammonia gas, negative 46.1 compound. Okay, here we go. HCl gas, 186.8 and 86.9. Triatomic gases, polyatomic gases, NH3, 192.5, and I'm going to check my ammonium chloride. If no, it doesn't have it in there, so we'll not worry about that. We'll worry about that later. Let's go back to, so we have some numbers to work with. We have some numbers to work with now. Remember, to calculate our delta H, we won't have this problem on the test because I'll give you the numbers already spelled out. That's the difficulty of doing this on a take-home. You have to find your numbers. So delta H would be products, negative 92.3 and negative 46.1, minus reactants, which is negative 314.43. So putting it through, 92.3, negative 46.1, plus a 314.43 would give us delta H is equal to positive 176.03. So sublimation is an endothermic process. Hopefully that makes sense. We have to heat this to make this gasify. Now, for our delta S, 186.9 plus 192.5 minus 94.6, producing two gases from a solid should also be an entropically favorable process. So delta S is equal to positive 284.8. So that's joules per mole Kelvin, and that's kilojoules per mole. So delta T is equal to delta H over delta S. We have to watch out for our units. So 176.03, we have to times that by 1,000 to get this into joules. We're dividing that by 284.8. So this is going to be joules per mole when all is said and done, and this is going to be joules per mole Kelvin. So joules per mole cancel out. We're given units of Kelvin. Hopefully, this will make sense. Hopefully, you won't give me an answer that is smaller than 1, because 1 Kelvin is cold. Going less than 1 would be very cold. Ammonium chloride would not last as a solid in any world. It would only last for a solid in outer space, if even that, if you gave me an answer of 1 Kelvin or less than 1 Kelvin. So the correct answer is not 176 over 284, but 176,030 over 284.8. So you get 618.08. 618.08 Kelvin, which, if you turn that into Celsius, which I don't ask you to, but is 345 degrees Celsius. So reasonably hot, hotter than it would take to boil water. Well over the boiling point of water. Now, how much ammonia would exist at 25 degrees? We need to find K, because remember, K, for this is products over reactants, it's going to be ammonia and HCl over a solid. Solids cancel out. We have 1. So to find the amount of ammonia, we can find K. To find K, we need to find delta G from delta G equals negative RT ln K. This is like the lab we're going to be doing, except a little bit backwards. Delta G equals negative RT ln K. So what is delta G at 25 degrees? We have our delta S, we have our delta H. What is our delta G at 25 degrees? So positive 176.03 minus 25 degrees is 298 Kelvin times 284.8 joules per mole Kelvin. We have to times 1 over 1,000 to get this into kilojoules. Get this in kilojoules because this is kilojoules per mole. Kelvin and Kelvin, that's so our delta G at 25 degrees is going to be a positive number. But it's going to be positive 91.1, we'll say 16 kilojoules per mole. Sorry, it's off the screen. So I did that 176 minus 298 times 284.8 divided by 1,000. That's our delta G. Delta G, as I said, is equal to negative RT ln K. So we do 91, sorry, off the screen, 91.16. We have to multiply by 1,000 because we want this in joules. We have to divide by R, 8.314 joules per mole Kelvin, and divide by our temperature, 298 Kelvin. All that gives us ln K. All that gives us ln K. We just got, oh, and we have to make this negative. So we got this to the other side. We divided both sides by negative RT. Negative RT. So 911, we'll say, 160 divided by 8.314 divided by 298. You get negative 36.79 equals ln K. Last step is we take the last 2 steps. We have to find K. So take the inverse natural log to both sides. So you get E. You get Okay, so our K value here is equal to 1.048 times 10 to the negative 16th. And finally, our K value is going to be the square root, our concentration of ammonia is going to be the square root of K. NH3 essentially is going to be X squared. So I'm going to square root this, square root that. I know this is a massive problem, massively difficult. You do that, square root 3, 6. You get what? 1.02 times 10 to the negative 8. That's your concentration of ammonia that would be present at room temperature. That was a massive problem. First, you had to find delta G from your delta H and delta S. Second, you had to find K using your delta G. And then finally, you had to use K to find the concentration of one of those. It's very trace, very small, but it might be enough to smell it. It might be enough. It's present. It's not zero. It might be enough. You get a faint ammonia-like odor when you're smelling ammonium chloride. Now, the problem 8. Using the following whiskey barrel reaction to answer the related question. Hydroquinone C6H6O2 and H2O2 goes to benzoquinone H2O. It's a process by which it's a peroxide which naturally is going to occur over time in the barrel, gets treated by some of the starches in the barrel, thus preventing the spoilage of wine and whiskeys. The reaction, what is the oxidizing agent and how many electrons are transferred, and then determine the cell potential. So breaking it down, this one is a little bit harder than, say, some of the other ones because you probably can't, it's a little bit harder to find just straight up these guys. You might be able to find them. Hopefully they're on the chart. Otherwise, we're going to spend some time looking for it, or I might just skip it. But okay. You notice we go from C6 to C6H6 to C6H4. So we've lost 2 hydrogens on benzoquinone and hydroquinone to go into benzoquinone, and we gained them in the presence of H2O2. The easiest way to maybe do this is split it into its 2 half reactions. If you've balanced one, you can balance the other. Balance one, you can balance the other. So 1 half reaction would be C6H6O2 goes to C6H4O2. H2O2 goes to 2H2O. In all these cases, we're only missing hydrogens. I can put 2 hydrogens here. Thus, I have to do 2 electrons. That's 2. I have to put 2 hydrogens here. And thus, this guy's going to get 2 electrons. So the first question is, which of these guys is the oxidizing agent? Which of these guys is the oxidizing agent? And how many electrons are transferred? The oxidizing agent is the guy that gets reduced. The oxidizing agent is the guy that gets reduced because he oxidizes something else. Remember, reduction is gain. Reduction is gaining electrons. So hydrogen peroxide is the oxidizing agent. Now, how many electrons gets transferred? 2 electrons. O2 minus, which is a charge of -1, goes to O2. O1 minus goes to O2 minus 2 times. So 2 electrons are gained by oxygen and 2 electrons are lost by carbon. Now, to look up the half reactions here, we'll see if we can get at least one of these guys on the standard molar enthalpy. I'm not sure. We can probably get one of these at least on the table. We'll see if we can get the other one. Oh, geez. Okay. I've learned my lesson. H2. No? Okay. Huh. Okay. Guess I'll have to go the long way. So scroll down. Once again, this is a disadvantage of using this big table. There's way too much data. Way too much data. Okay. Nope, nothing yet. Okay, let's see. There's hydrogen. Okay. There's oxygen. Okay. 1, 2, 3, 4. Okay, this is our hydroquinone, benzoquinone. We found that one of 0.6992. Now so hydrogen peroxide is probably above that. So somehow I missed that. I know hydrogen peroxide is a pretty powerful oxidant. So the question is just, where is that? I think that's the reason I use this table, because it had that one on it. Oh, wait. My goodness, it's down. This is an opposite order. It's opposite order. I want to keep going down. That's why. There's O2. Chlorate. There we go. H2O2 goes to water. So that's 1.78. So looking up on a table, you'll have a table. You'll have a table much, much smaller. All the data can be got directly from the table. Okay, so I've looked up on my 2 values. Thankfully, that didn't take us 20 minutes. Remember, this one appears as written. This one appeared in the reverse order. to calculate E cell, the E cell, we do the reduction minus the oxidation. The one that appears as a reduction minus the one that appears as an oxidation, the one that appears opposite as on the table. So to calculate the cell potential is just 1.78 minus 0.6992. You do that, you get this E cell as 1.0808 volts. Done. That's all there is to that. Now, the positive cell potential is indicative of a spontaneous reaction. A negative cell potential would be indicative of a non-spontaneous reaction. So, some reactions will be not spontaneous. Don't assume all the numbers will be positive. Double check and see what the reaction actually says. The last problem on the test, besides the bonus, was 0.0808. If the concentrations of hydroquinone, benzoquinone, hydrogen peroxide are as follows. What would be the non-standard voltage? So this one is E non-standard equals E cell. What is it? Is it plus RT over NF? Or it might be minus RT. Yeah, it's minus RT over NF ln Q. Based on that equation, our reaction, our Q expression is going to be, I'm going to say, C6H4O2 over C6H6O2 and H2O2. So hydroquinone 0.001, benzoquinone 0.1, and hydrogen peroxide 5 times 10 to the negative 7th. So let's look at that, and then it's 25 degrees. Let's just one. Mouse go. Oh, jeez. Let's double check the equations. I don't want to start doing this and then get that all funky. No, it's E. It's minus. Yeah, it's minus. Okay. Okay. Go to dot cam for the last time for this. So we got our E cell. That's our E cell. Our temperature is 25 degrees, so it's 298. N, remember, is the number of electrons transferred. We figured that out in the first part, which was 2. And our Q is our products over reactions. We don't include water because water is a pure substance, a pure liquid. We don't include pure liquids or pure solids. So first things first, what is our Q? 0.1 divided by 0.001 and 5 divided by 5 times 10 to the negative 7th. So our Q is something like as 2 times 10 to the 8th. So like 2 times 10 to the 8th. So a big number. But the idea here is that this is not very high concentration. But the idea is that when peroxide appears, it can ruin the flavor, which is why aging in the barrels is sometimes good because you're allowing this to decompose to a very low concentration. So our E cell 1.0808 minus 8.314 times 298 divided by 2, 96485 ln 2 times 10 to the 8th. Let's figure out what all this term is. 8.314 times 298 divided by 2 divided by 96485 times ln 2 times 10 to the 8th. In some books, they will have simplified this as a number over n log. I don't know why they do it. I don't like it. I don't like it. But 2.4 is 0.245, negative 0.2454 volts. So 1.0808 minus 0.2454 would be, the voltage is 0.8354 volts. Still pretty spontaneous, still pretty reasonably high voltage, even at this massive concentration of benzoquinone versus hydroquinone and hydrogen peroxide. That is the last problem on that test. I will quickly summarize the types of problems from these 3 chapters, and then I will go over some real quick, at least, review of kinetics. So when you get a nuclear chemistry problem, you can be like, oh, okay, that's not too bad. But that was the test. It said it was a bit harder because it was take home. Please note, you will have a page of just E-cell potentials, but it will only take up a full page. That'll be on the useful information sheet on the back of your paper. Whenever you need a delta H or delta S value, it will be provided. If one is not provided, assume you can get it through E-cell. Get it through E-cell. So let's look at what type of reactions we have. We can look at delta S by observation. So we could find what is a delta S just by looking at the equation. And this is the case where more gas on right is positive entropy. More gas on the right. Solids don't really count. Liquids don't really count. More gases on the right than on the left would be an increase in entropy. So like this guy, zinc carbonate solid going to zinc oxide solid plus CO2 gas would be positive entropy because one gas is greater than 0 gas. Even though this is way more complicated than zinc oxide, the amount of you get from CO2 alone blows them out of the water. So you can find delta S by observation. You need to be able to find, there's no problem that it's just going to be delta H or delta S, but you need to be able to find delta H and delta S pretty simply. They are equal to, of the systems, they are equal to the sum of the products minus the sum of the reactants. Pretty straightforward. Pretty straightforward. The final state minus the initial state. Don't overlook that. There will be plenty of equations where you need to find delta G at a temperature. Maybe it's at 25, maybe it's at some other temperature, but delta G is equal to delta H minus T delta S. Don't forget, this is often divided by 1,000 because of units. This is in joules. Delta H is in kilojoules. And delta G is in kilojoules, typically given in kilojoules. So we have to make sure everything's in kilojoules. You might be asked, what is the entropy of the universe? That is simply a rearrangement of this guy in that we have delta S minus delta H over T. And this is typically times by 1,000. Once again, because entropy is in joules. It's just a rearrangement. But for most of those problems, you'll have to find those two values and plug them into either this or this. Make sure your temperature is in Kelvin. Pretty straightforward. We will most likely see an equation like this. Either we're solving for delta G given a K, or we're solving for K given a delta G. Make sure you don't find ln K, that you actually find the K expression. Rearranging it. If I'm solving for K is actually equal to the inverse log of negative delta G divided by RT. That's typically times by 1,000. If I'm finding delta G, it's just this whole thing, then divide by 1,000. Because remember, kilojoules, joules, kilojoules, joules. 8.314 joules per mole Kelvin. And then we may use this equation, but there's no guarantee we'll use this equation, that delta G is equal to delta G standard plus RT ln Q. Probably not. You may at best use this either one time for E non-standard or one time Gibbs non-standard. You probably won't have a question about both. Typically, you'll either be able to easily or quickly find the Gibbs or E cell standard, and then you'd go from there. I'd give you, how do you recognize this one? Typically, I'll ask for something non-standard. I'd specify non-standard in the answer, and I'd give you some sort of concentrations. Keep in mind, how do we set up Q? Q is our products over reactants raised to the power of their exponents. I don't know what the exponents are, so I'm not going to include them. But solids and liquids don't count. That's the majority of our equations from the thermodynamics chapter. Well, there's one more. And that's the temperature one. The temperature equals delta H over delta S. Remember, that's typically times by 1,000 because of kilojoules versus joules. So that's the majority of the types of questions from that chapter. There is a few things you might have to remember, but for the most part, most of those are multiple choice. Got to remember maybe that delta G non-standard, when that equals 0, the reaction is at equilibrium. So the reaction essentially stops. The reaction will be approaching from delta G negative. It's going to approach 0. Reaction always swings to try to get to 0. For the next, if we have the idea of oxidized versus reduced, where the oxidized is the reducing agent and the reduced is the oxidizing agent, and this is electrons gained, electrons lost. You need to be able to balance a chemical equation. So work one out. Remember, you have a cheat sheet available to you. What you got to do is you have to be able to at least balance one, if not two chemical equations. Work one out. Have the steps written down. What I would suggest you use that cheat sheet for is not memorization of little tidbits here, but working out some trickier problems. Show how you solve it. If you do that, you can look and say, oh, this is where I got this number from. This is where I got this number from. This is where I got this number from. So you don't have to keep guessing. You can know, oh, I just copy over different numbers and there we go. The E cell standard is the E of the reduced minus the E of the oxidized. We're going to use the numbers straight off the table, and just subtract the 2. Straightforward. This is the one time coefficients don't matter. This is the one time coefficients don't matter. You don't need the equation balanced. You just have to find what is the two half reactions. From there, we have a few equations. We have delta G equals negative NFE. Once again, you have to divide by 1,000 to get correct units, to get this in kilojoules. N is the number of electrons. F is a constant. You will be given it. From there, we can say that E equals RT over NF ln K. Don't expect a ton of problems like that, but there might be one. And also the E equals E cell standard minus RT over NF ln Q. As I said, I'm either going to do one of those or one of the Gibbs version. Definitely not more than one. It's a pain in the butt equation. And it doesn't change the value from the E cell by too much usually. But it does change it. And the other big equation here, the last real equation here, is our charging. If I want my mass, it's voltage, it's current times time times molar mass over NF. If I want time, it's going to be time is equal to mass divided by current and molar mass times NF. That's the one where it's saying, oh, I want to electroplate titanium onto the surface of this metal. How much titanium could I electroplate with this current over this time period? The time is always in seconds. You sometimes need to convert that from seconds to minutes or hours. but you need a molar mass, depends on the element, and typically we're going from the most the charged state down to neutral. So if I'm going from, for example, lead 4, N is going to be 4. If I'm going from calcium 2, N is going to be 2. We're probably going to a neutral state. We're usually going to a neutral state when we electroplate. So if I had lead 2, then obviously the N would be 2. We're not going to go lead 4 to lead 2. We're probably going to go lead 4 all the way to lead 0, or lead 2 all the way to lead 0. So you can just look at the charge state to figure out what is the N. What is the N? The molar mass is just going to be the molar mass. But those are the chief equations relating to the thermodynamics chapter. There is a few more things of the nuclear chemistry. We don't have a whole lot of nuclear chemistry. Quick reminder, alpha is a 4-2 particle. Beta is a 0, -1 particle. Positron is a 0, +1 particle. Gamma is a 0, 0 particle. For nuclear addition, it's going to be something like, and a neutron is 1, 0. If I said some guy, I'll call it element X with a number like 32, 5, and I've had N, 1, 0. And I say, this goes into alpha 4, 2 and something else. What do you got to do? 32 plus 1 is 33. So it goes to 33 over 5, and then it breaks apart. It breaks apart to alpha, so 4 and 2, and this has to add and something X and Y. This top has to add up to 33. So 33 minus 4 is 29. 5 minus 2 is 3. So this crazy molecule that I'm imagining would be lithium 29. Doesn't exist. It's a bad example. But the idea is you fill in the blank. You fill in the blank with the thing that adds up to the right side. The right side and the left side have to add up. If you do that, that is transmutation. That's all you have to do. You figure out what this is by looking at what this is. By looking at what that number is. And kinetics. There's 2 parts to the kinetics. You have ln 2 over t1 half equals k. And you have then ln a sub t over a 0 equals negative kt. So let's say half-life iodine. And let's say iodine 131. I-131 has a half-life of 8 days. So to find the K, you would take ln 2 divided by 8. And that's going to be in units of days. So ln 2 over 8 is going to be 0.0866. And if I ask what percentage would be left after I don't know, a 30-day month, after 1 month, we'll say 30 days. You would take negative k times 30 times 30, and then you'd solve this as a percentage. So we have our K times 30. We have to make it negative. And how do we get rid of this natural log? We do the second. Oh, I do my inverse log. And what percentage would be left after 30 days? 0.074 times 100 to get into percentage. 7%, 7.4% would be left after 30 days with a half-life of 8 days. So it doesn't matter what situation you have, what half-life you have, you can figure it out. It's all the same. You just need to make sure the units of time match up. If I gave you 1 year, you would have to turn that into days. That would be 365 days, or 365 and a quarter days, or whatever. If I gave you so many minutes, so many hours, say after 4,000 hours, you would have to turn that into days. 4,000 hours would be 166 days. You just have to make sure the units of time match the units of time in the half-life. If this was instead of 8 days, but hours, I would then have to turn 30 days into however many hours we had. So we just have to make sure we watch the time. But that is the process. As I said, I didn't have a ton of stuff for us today. We finished the take-home test. We went over all the different types. So go ahead and work on your cheat sheet. Put a few useful informations, but I'd say mostly show how you work out the problems. Show how you work out the problems, because that's going to be the big thing. It's going to be the big thing. If you have any questions, you feel free to ask now. If not, I'm going to end the meeting in a few minutes time.